Hello, welcome to Machine Learning at Home. Today I will speak about hypervolumes. As you know, multivariate data, which is used for machine learning, could be represented as a cloud in a multi-dimensional space. This is very hard to imagine, but some calculations are possible. So very frequently we project multi-dimensional space with some projection or dimension reduction tool and use it afterwards. But this is possible to work with it directly. Of course, this is extremely slow if number of dimensions is high. But if number of dimensions is relatively low, like 2, 3, 4, 5, 6 maybe, these calculations are possible. And in R, there is a package hypervolume. So library hypervolume. So this is a set of tools which calculate things in multi-dimensional space. And if we load it, it will load RCPP package, and it's slow, as you see. One of the slowest loading as I see in R. And now it's ready. So now we do some hypervolume calculations on a very well-known example of same ARIS data which I use almost for everything. So if you remember, there are three species. Two species are close together, one species is more apart. How about hypervolumes on the species multi-dimensional clouds? Let us calculate it first. So first of all, I will calculate each hypervolume for each species. So I need to separate species, first of all like iris, and then I will select only those rows which species value is equal to some species. For example, we start with versicolor. And then I will need only 4 first columns, because 5th column contains the species name. And this is what I started from, and I will use hypervolume box command, which is calculating this hypervolume first. So sounds like everything is good enough, and then we need to name the result. Result will be, for example, H for hypervolume, VE for versicolor. HVE will be name of our object. Okay, let us do it. As you see, it's not very fast. So this is a first hypervolume box, and we need 2 more, like for Virginica. And name should be different. For example, VI. And finally for Setosa. And name will be again different. Okay, now we have 3 boxes which are kind of representations of hypervolume, which is easy to use in further calculations. Now, most important, we need to calculate some statistics. What about overlap between boxes? Well, theoretically, overlap between versicolor and Virginica should be much higher than overlap between Setosa and any of the species. Let us demonstrate it. So, first of all, we need to use the command hypervolume set. And for that command, we need 2 arguments. For example, we use Virginica and versicolor. And to avoid some long calculations, we should say check memory equal to false. Okay, and we'll read the some object. So for example, HVV. So will be VIVE object contains information of set between versicolor and Virginica, the hyperclouds. Let me see how it works. Okay, as you see, it's still kind of slow, and we need another stuff. For example, we can use Setosa as a second argument, and maybe will be like a HVISE. Okay. Finally, we can calculate overlap. So hypervolume overlap statistics, and that statistics will be applied first to our first set HVVE, which represent two species, Virginica and versicolor. So my prediction, the overlap should be significant. Let me see it. There's some overlap, so you can use, for example, Jacquard coefficient if you like, and maybe other coefficients which are also representatives. And next one, what about Virginica and Setosa? I guess that overlap should be either much smaller or simply absent. Yes, as you see here, Jacquard is 0, so no overlap whatsoever. Exactly what its typically data is. So you can use these methods for data with, unfortunately, not very high dimensional structure. So my practical approach says that like a number of dimensions more than 5 is complicated. You need a very powerful computer to do some larger dimensions. But still, this is useful. For example, at first step, you can reduce number of dimensions with some tool, for not to 2, but like to 3, 4, or 5. Then your data will be much more precise. And then you use hypervolume. This is two-step approach. And we can also calculate distance between hyperclouds, which I like a lot, and it will be done in different way. So I will use the command hypervolume distance, and then we use initial boxes HVI, HVE. So distance in that case will be 175, and if you use Setosa as second box, distance will be much more. So distance also represent this nature of our object. Just to remind you, VI and VE, Virginica, versicolor, are very close together, whereas Setosa SE is much more apart. So as you see, it's applicable, it works. The only thing which I found myself, it's slowness if data is large, especially if dimension number is more than like 4 or 5, and data size also is large. This is very useful package, and I hope it will develop further, and soon we'll have some good results even for bigger objects. So again, hypervolume, there are much more commands within a package, and you can search it for yourself. So again, this is hypervolume calculations.